So here in section 9.4, we're going to look at our sample evidence, the p-value, and then the decision and conclusion that we can make. So the p-value is a measure of how extreme our sample information is. To get that p-value, we have to find something called a test statistic. So if you're testing the mean, then your test statistic is going to be x bar minus your hypothesized mean divided by sigma over root n. That's if sigma is known. If sigma is unknown, then you're going to use S down here instead of sigma, and then that's the t-distribution. So if you're doing a test for proportion, then your test statistic is going to be a z-value. P prime is your P prime is your sample proportion. P0 is your hypothesized proportion, and then this is the standard deviation of the sampling distribution. So this is standard deviation of the P prime distribution. And then down here in the denominator here and here, those are the standard deviations of the x bar distribution. So the sampling distribution for the sample mean. And in both of these cases, this is a z-score or a t-score of the sample. So the test statistic here is the standard score of the sample evidence, z or t. And so if that is a bigger number, bigger positive or bigger negative, that's a more extreme sample. So, and then your p-value is defined to be the probability that another sample would be as or more extreme than the given sample if we know the null hypothesis is true. So geometrically, that's the same as the area past the test statistic. So let's take a look here at the possibilities. If we're given a lower tailed test, that's when your alternative hypothesis is mean less than a number. And then your null hypothesis would be equal or greater than equal that same number. So in that case, your test statistic will typically be on the left-hand side, and then the p-value is the area past that test statistic on the left-hand side. So your p-value is that shaded area there. And that's a measure of how extreme your sample is. If your p-value is smaller, that means your test statistic is farther out away from the middle, more extreme sample. If your alternative hypothesis is mean greater than a number, mu0, then your null is going to be equal or less than equal. And in this case, we're expecting our test statistic to be on the right-hand side over here, and then the area past is right there. So the p-value is that green shaded area. That's an upper tailed test. So lower tailed, your shaded tail, they call that the tail of the distributions on the left. For an upper tailed, the shaded tail for the p-values on the right. For a two-tailed distribution, that's when your null is equal and your alternative is not equal. And in this case, our test statistic could be on the right-hand side, or it could be on the left-hand side. And then the p-value is both of those pieces together, so actually each piece is half of the p-value geometrically. And then we can use the distribution calculator to find those areas. So let's go ahead and put this to work, and we'll find some p-values here. So we want to, got 5 years ago, the graduation rate in the district was 73%. Since then, the superintendent instituted changes to improve student success. This year, 342 out of 450 graduated. Test the hypothesis that the graduation rate increased at the alpha 0.05 level, and we are computing the p-value. So this example we looked at before, remember our H0 and HA here. So we wanted to show that the graduation rate increased. So that would be p greater than 0.73, and then your null would be p, the proportion of graduated, was less than equal 0.73. And then our p prime, our sample proportion, that's the 342 out of 450. So 342 divided by 450. Compute that on the calculator. So 342 divided by 450 is 0.76. And now we want to go ahead and compute our test statistic, and that will be this formula here. So let's grab that and bring it down. So our P prime on top there is 0.76 minus P0, our hypothesized proportion is the 0.73 from 2020, and denominator we've got 0.73, 1 minus 0.73, and then our n is 450, total sample size. So let's compute this on the calculator. So I'm going to clear that out. I'm going to do horizontal fraction, alpha y equal enter. On the top we've got 0.76 minus 0.73, and the denominator we have a square root, and then I'm going to do alpha y equal enter again to get horizontal fraction. So on top we got 0.73 parenthesis 1 minus 0.73 close parentheses down on the bottom 450 and enter. So 1.433. Now, usually we'll round those z-scores to 2 decimal places. You can take it out more. So 1.43. So here's our sampling distribution. We've got 0 in the middle. So 1, 2, 3 to the right. So 1.43 would be about right here. And so the p-value is going to be the area past that 1.43. And we can find that with normal CDF. So this will be normal CDF. Our left or lower bound's 1.43. Our upper bound, we're going out to infinity, we'll use 10,000. Our mean is 0 and our standard deviation is 1, and we know that because we've converted to z-scores. So that's always 0, 1. So let's compute this on the calculator. So second variables, we want normal CDF number 2, lower 1.43, upper 10,000, paste, enter, 076358, so 0764. So there's our p-value. Test the hypothesis that the graduation rate has changed at the alpha is 0.05 level. Compute the p-value. So the only thing that's going on here is that our H0 is going to be p equals 0.73, and our HA is going to be p is not equal 0.73. So it's an equal, not equal test instead of a greater than, less than equal. So that means that we could have a p-value on the right or on the left. So we're going to mark off that 1.43. Our test statistic's still the same. None of this changes. But it could be positive or it could be negative. So this is p over 2, and this is p over 2. So that just means that our p-value here is going to be 2 times the 0764. So 2 times 0.0764, 1528. So, and then what do these represent again? This means a 7.64 chance of getting a sample that's as extreme or more extreme than this sample, 342 out of 450. This one says if you're doing a two-tailed test, the probability is 15.28%. So I'll write that down here. I've got room. So 15.28% chance of a sample as or more extreme. Than the one that we have. So it's a measure of how extreme the sample is.